More than 5 decades have passed since humanity last ventured beyond low Earth orbit. Between 1969 and 1972, NASA's Apollo missions carried 12 astronauts to the lunar surface, with Apollo 17 marking the final chapter of that era in December 1972. It has now been more than 53 years since humans last set foot on the moon. Now, NASA's Artemis program is beginning to revive that legacy. Named after Artemis, the twin sister of Apollo in Greek mythology, this new lunar effort is not simply about brief visits. Instead, it aims to establish a sustained human presence on the moon, to make use of its resources, and to turn it into a testing ground for the technologies that could one day carry us onward to Mars. Artemis I. NASA's uncrewed test flight in late 2022 proved the core systems by sending the Orion spacecraft on a 25-day journey around the moon and back, traveling over 2.25 million kilometers and enduring the harsh realities of deep space. With that success in hand, Artemis II will be the program's first crewed mission. As early as April 1st, pour Astronaut, Commander Rate Wiseman, Pilot Victor Glover, mission specialists Christina Koch and Jeremy Hansen will launch for a high-stakes lunar flyby, testing and validating the hardware with human passengers. At the center of this mission are two engineering marvels: the Space Launch System rocket, or SLS, and the Orion spacecraft. The SLS is NASA's most powerful rocket to date, a towering 322-foot launch vehicle capable of generating 39 meganewtons of thrust at liftoff, about 15% more than Apollo's Saturn V. Its core stage is powered by 4 RS-25 engines, each producing 1.8 meganewtons of thrust and burning a combination of liquid hydrogen and liquid oxygen. Attached to either side are 2 solid rocket boosters, each delivering 14.6 meganewtons of thrust and providing the bulk of the power during the first 2 minutes of ascent. Above the core stage sits the interim cryogenic propulsion stage, which uses a single RL-10 engine, also fueled by liquid hydrogen and oxygen, delivering 110 kilonewtons of thrust to place the crew capsule on its trajectory toward the moon. Nestled at the very top of the SLS is Orion, the spacecraft designed to carry the crew. It takes the familiar capsule shape of Apollo, but is far more advanced, with a crew module offering about 9 cubic meters of habitable space, roughly comparable to a small van and sufficient for 4 astronauts. Inside, it features modern digital flight controls, a glass cockpit interface inspired by commercial aircraft, onboard computers, and manual backup controls for contingency situations. It also includes a complete life support system that regulates air, water, temperature, and waste, along with storage and personal living space for the crew. Beneath the crew module, engineers have integrated a robust heat shield made from specially engineered materials designed to absorb and dissipate extreme heat during re-entry. This shield plays a critical role as Orion returns to Earth, protecting the capsule while it plunges through the atmosphere at immense speed. Attached below is the European Service Module, developed by the European Space Agency, which serves as the spacecraft's power and propulsion unit. It houses the main engine, 8 smaller thrusters, fuel tanks, and 4 large solar arrays that generate electricity throughout the mission. It provides in-space propulsion and carries essential consumables such as water, oxygen, and nitrogen needed to sustain life. Mounted on top of the crew module is the Launch Abort Tower, a safety system designed to rapidly pull the capsule and crew away from the rocket if a serious issue occurs during launch or ascent. With the hardware in place, we can now follow the Artemis II mission profile, A carefully planned 10-day journey that begins at Kennedy Space Center's Launch Complex 39B in Florida. At liftoff, the SLS ignites its 4 main engines, along with its twin solid boosters, sending Orion, with 4 astronauts on board, upward with immense force. Within 2 minutes, the solid boosters separate, and about 6 minutes later, the core stage shuts down and detaches. The upper stage then continues the ascent, placing Orion into an initial low Earth orbit. The first step toward the Moon. Once in orbit, Orion separates from the upper stage, and the crew begins a thorough check of all onboard systems, confirming that life support and communications are functioning as expected before committing to the journey ahead. After roughly 2 days in Earth orbit, the European service module will ignite its main engine once more, performing the critical trans-lunar injection burn that sets Orion on its path toward the Moon. This burn will place Orion firmly on its path toward the Moon. The mission follows what is known as a free return trajectory, a carefully designed flight path that uses the Moon's gravity to bend the spacecraft back toward Earth without the need for a major engine burn. In practical terms, it means that even if something were to go wrong with propulsion along the way, Orion would still be carried home naturally along this looping route around the Moon. It is an elegant solution, shaped by orbital mechanics rather than brute force. But like all deep space trajectories, it still depends on every system performing with near-perfect reliability across vast distances. Once committed to this trans-lunar journey, Orion will coast through space for about 4 days, but unlike earlier missions, it will not settle into a low lunar orbit. Instead, it follows a much wider arc. For perspective, NASA's Lunar Reconnaissance Orbiter circles the Moon at roughly 50 kilometers, mapping its surface in remarkable detail. While the Apollo missions operated at around 110 kilometers before descending, Artemis II extends far beyond both of these paths. During its flyby, Orion will pass the far side of the Moon at an altitude of about 8,000 kilometers. From this distance, the Moon will still dominate the view, vast and textured, while Earth, nearly 370,000 kilometers away, will appear as a small, distant blue point suspended in darkness. At that point, the Artemis II crew will be farther from Earth than any humans have ever traveled. It is a distance measured not just in kilometers, but in separation, a moment where human presence stretches to its limit. As Orion curves around the Moon, it will cross above the far side, a heavily cratered and ancient landscape that never faces Earth. From this vantage, astronauts will be able to observe and capture images of immense impact basins and the darker volcanic plains known as Lunar Maria, formed billions of years ago when molten lava flooded those basins, leaving behind the surface patterns we still see today. Although the lunar flyby lasts only a few hours, it represents the most defining moment of the mission. Once Orion passes the Moon, it will rely on gravity to curve back toward Earth along the same free return trajectory. The journey home will take another 4 days, during which the crew will continue monitoring spacecraft systems, carry out radiation and microgravity experiments, and gradually prepare for re-entry. By around day 9, Orion will begin aligning itself for its descent through Earth's atmosphere. Before re-entry, the crew module will separate from the European service module, discarding the propulsion system that supported it through deep space, and then use its onboard thrusters to correctly orient the heat shield for the intense phase ahead. As Orion approaches Earth, it will be traveling at nearly 11 kilometers per second, fast enough to generate extreme heating as it encounters the atmosphere. To manage both the thermal load and the physical forces, it will perform a skip re-entry, briefly dipping into the atmosphere, rising back out using aerodynamic lift. and then descending again for its final entry. Much like a stone skipping across water, this technique helps reduce the stress on the crew and distributes the heat over a longer path. So, Orion's heat shield will endure temperatures of around 2,760 degrees Celsius, roughly twice the temperature of molten lava and approaching half the heat of the sun's surface, making it one of the most demanding re-entry environments ever faced by a crewed spacecraft. Even after decades of experience, returning from deep space at these speeds remains one of the least forgiving phases of any mission. As Orion descends into the lower atmosphere, its parachute system deploys in carefully timed stages. First, small drogue parachutes stabilize and slow the capsule, followed by 3 large main parachutes that gradually bring it down toward a controlled splashdown in the Pacific Ocean, off the coast of California. There, recovery teams from the US Navy and NASA will retrieve both the capsule and its crew, bringing their 10-day journey around the moon to a close. To maintain constant communication throughout the mission, NASA will rely on 2 major systems: the Near Space Network and the Deep Space Network. Together, these global arrays of satellites and ground antennas coordinate to provide continuous communication and navigation support at every stage of the flight. Control of these networks is carefully managed from Mission Control at Johnson Space Center in Houston, ensuring Orion remains connected as it travels farther from Earth. While in low Earth orbit, Orion and the SLS operate through the Near Space Network. But once the spacecraft performs its translunar injection, responsibility shifts to the Deep Space Network, which guides and tracks Orion across the vast distance to the Moon and back. For most of the mission, the crew will stay in near constant contact with Earth. Aside from a planned blackout period when Orion passes behind the Moon and loses direct line of sight, during the flight, NASA will also test a laser-based communication system, periodically transmitting data to demonstrate the potential for much higher speed connections, whether through radio signals or optical links. Orion will continuously send back voice, image, video, and detailed spacecraft health data. Across these distances, communication is never truly instantaneous, but a continuous exchange across space, linking a distant crew back to a planet nearly 400,000 kilometers away. All of this data is processed, compressed, and handled by ground systems back on Earth. Beyond its 4-person crew, Artemis II also carries several small secondary payloads, including 4 CubeSats developed by international partners under the Artemis Accords. Each of these compact satellites, no larger than a shoebox, will be deployed into high Earth orbit just a few hours after launch. Their objectives differ, but many are focused on studying the radiation environment surrounding Earth, testing new materials, and demonstrating communication and navigation technologies that could support future deep space missions. As for the crew, Artemis II brings together a combination of experience and historic representation. Commander Rate Wiseman, a U.S. Navy aviator and veteran astronaut, previously spent over 165 days aboard the International Space Station in 2014, and later led NASA's Astronaut Office, overseeing flight operations and crew assignments. Pilot Victor Glover, a former Navy test pilot, flew on SpaceX's Crew 1 mission, spending 168 days in space, and will be responsible for Orion's flight control and navigation. Mission Specialist Christina Koch, who holds the record for the longest single spaceflight by a woman at approximately 328 days, will oversee scientific experiments and assist with spacecraft systems throughout the mission. Mission Specialist Jeremy Hansen, an astronaut from the Canadian Space Agency and a former fighter pilot, will be making his first journey into space, focusing on scientific operations and supporting onboard systems during the flight. All 4 astronauts have undergone an intensive Artemis training program. They have accumulated thousands of hours inside Orion simulators, practicing system operation, emergency scenarios, centrifuge session, and even underwater spacesuit training. Every phase of the mission has been rehearsed in detail, from launch procedures to ocean recovery, using full-scale mock-ups of both the SLS rocket and the Orion capsule. Taken together, they represent the most thoroughly prepared crew for a lunar mission since the Apollo era. On launch day, they will suit up, travel to Launch Complex 39B, ascend the mobile launch tower, and board Orion at the top of the SLS as ground teams complete final preparations and the countdown enters its final hours. Artemis II is no longer a plan on paper. It has now launched. In early April, the Space Launch System lifted from Kennedy Space Center, carrying 4 astronauts beyond low Earth orbit for the first time in more than half a century. What had long been a projection has become an event, a trajectory already unfolding in real time. Over the course of roughly 10 days, the crew is following a wide free return path around the Moon, moving farther from Earth than any humans since the Apollo era. Each phase of the mission, from life support validation to deep space navigation, is no longer theoretical. It is being tested now, under the conditions it was designed for. This shift matters, because Artemis II is not just demonstrating capability. It is confirming whether the architecture of the Artemis program can function with humans on board. Systems that performed well in Artemis I are now being evaluated under the added complexity of crewed flight, where margins are narrower and decisions carry different weight. And as this mission progresses, attention has already begun to move forward. Artemis III, once expected to deliver the next lunar landing, is now being reshaped. Rather than committing immediately to the surface, the mission is increasingly focused on validating the systems that will make such a landing possible. This includes in-orbit testing, docking procedures, and integration between Orion and commercially developed landers, such as SpaceX's Starship Human Landing System and Blue Origin's Blue Moon. These steps may appear indirect, but they reflect a deeper shift in strategy. From attempting a single milestone to building a system that can operate repeatedly and reliably. If that progression holds, the first Artemis lunar landing is now expected to follow with Artemis IV, currently projected for the latter part of the decade. That mission is planned to target the Moon's south polar region, an area of particular interest due to the presence of water, ice, and the potential for long-term resource use. Seen this way, Artemis is not defined by a single landing. It is a sequence, a gradual expansion of human reach, from Earth orbit to lunar space, and eventually to the surface itself, with each step designed to support the next. And with Artemis II now underway, that progression has moved beyond preparation. For the first time in decades, humans are once again operating in deep space, not simply passing through it, but beginning to understand what it takes to remain there. This is no longer a return. It is the beginning of a different kind of presence. And what follows will depend on what we learn from where we are now.